Hi everyone, I'm Zhang, and today I'm presenting eliciting the dynamic regional banking from banking supervisors. And I'm presenting here as a Zhang from Northeastern University, and also with my professor Mikhail Oyed. And acknowledgement. This study builds on extent of the Pavlov and Oyed and financial instability through the eyes of Federal Reserve Bank supervisors. And whether relevant, we acknowledge the use of research artifacts from Pavlov and Oyed, and also grateful for financial support provided by the Northeastern University. So comes from the motivation parts. So we do have a lot of the sophisticated and very fancy financial models related to our financial part, but we do not have kind of the expert insights regarding our complexity and the richness in our financial part. So that's basically the start of our project. And so basic step for a loop or for a diagram to express the financial problem will be first identify the problem itself. So we kind of discuss to set analyze boundaries and then list the variables that's maybe considered or related to the problem itself. Like list different variables that's related to the problem itself, and then we draw the graph and discuss, right? And maybe some kind of like positive or negative links between the nodes itself, and then we construct a causal loop diagram. This is where it starts, and we do get some graphs over time, right? And this is kind of very intuitive. We get like asset price. We do not want it to increase too high or decrease too high, right? We kind of want a certain range that's for asset price or liquidity. As time flows, it will went smoothly up, right? So whether it went too high or too low is fear, right? And this is kind of the graph we are getting from the workshop. And then when we get more nodes to the system itself, and from workshop, maybe this is the kind of more detailed graph or a small system that we have discussed for a causal loop diagram, right? And then this is the more clear version of the loops that were a small system that's you can see. We can get some certain nodes that's more impact for the other nodes, like asset price, for the losses, and for the ERM. We kind of get this loop. We can import to them like for now we can import them to a certain like commercial software like Winsome. If you have noticed or familiar with this kind of software, and we can actually detect the cycles that run through the bunch of nodes, right? For like we have 14 nodes itself, like here, and when we can detect the circles that have run through each node, and then we can get the degree. We can get the in degree and out degree, and also we can add them together, but that's all, right? So based on this point, that's also we kind of have the visualized part of like a dynamic one. We can see actually the adverse shock to technology. We can see some of nodes like spreads, asset price is running low, and some other price like some other nodes like capital is running high, and credit risk is running high, right? And also other bunch of other graph that you have made the adverse shock to regional economy, right? And this is actually another software called Loopy, and which is also used for like visualization for a small system like this. And then also a bunch of more. And this is basically the work that we continue to analyze more depths, analyze for like a small system, maybe for financial analysis. And for the first step, we based on the software we got for now, like Winsome, we do detect circles in all the nodes itself, and then innovative part we did is we actually detect the positive cycles and the negative cycles for each node. This is very important because, as you can see, for some certain of nodes, like the short-term counterparty funds, you do have a balancing nodes, the positive circle and the negative circle, they are equal. But for the other nodes, you can see almost all the other nodes itself, funding, credit risk, deposits, regional economic conditions, it's all imbalanced. Like negative circle is slightly more than the positive cycles. But for one node's operational risk, the positive circles is larger than the negative circles. We do think this is interesting because there's no software or there's no other ones to find the connections between the nodes itself and in the whole system. So and then we do is like we figured out how to count all the cycles that's in the system. Like for the data input part, we do have a certain kind of edge and polarities. This is very basic one, right? So we do not have certain like so many data you have input system to imply the system itself. We only need is kind of node A and node B and their relationship. Then we can construct a small system. So as you can see, this is very simple input. You can add your edge, your polarities, and then you can get the system run itself. So since we kind of get the edge and the polarities, we can construct a graph like this. And for the green line, which means that it's positive relation, and for the red lines, it's negative, right? So we kind of construct a graph like this, and similar to like the Winsome, you get that one. But we do have nodes like here for the nodes positive and negative detections, and also for all the cycles that have in this small system. Like take for example, as you can see up here, efficiency and expense and technology is a triangle, right? And when the start point is efficiency and then goes through the expense and technology and then to the efficiency itself, we call it like a loop. So as the start point and end point is the same nodes, so we detect all the cycles have within our systems. So and then we kind of set all the node value to value 1, and for positive loops, we set it as a positive 0.1, and for negative, we set it minus 0.1, and then we give the system inputs and let it run itself. And this is how we get, we kind of get the degree certainty, between certainty, and closeness certainty, and a bunch of other factors itself. So we clearly see that from the nodes or the graph that we have constructed, we certainly see that some of the nodes are more important, or the connection between the nodes itself are more have different impact or have large impact for the other nodes. So that is also clearly shown in our data. And since we have a bunch of the simulation, and also we let the system run like the 15 times or 100 times, we can get a kind of the correlation map between the nodes itself. As you can see, the red one is actually positive and the blue one is actually negative. As you can see, we kind of get the relationship between each nodes without any data input. And we just imply this data by the relationship between relationship between the nodes itself. And then this is how the data we get. And even more, we run this data by like, I would say 100 times, and then we kind of will get the distribution of the nodes itself and the value itself, right? So this is the graph. We set the nodes the value and see whether it's the implied or a certain distribution for the nodes itself, right? So we do think that we found a certain pattern of the value distribution, I would say, because after synthesize, I think that's most of the data itself between nodes is kind of bimodal, I would say, and the blue one on the left graph. The blue one is the original data, and the yellow one is the synthesized data. So as you can see, even clearly for in the right graph, and for almost all the nodes value, you do get a bimodal and bimodal distribution for nodes, right? And this is like the simulation or the average nodes value for one simulation, and we think that since we can get of the one simulation data, how about like we run it like the 1,000 times? And this is actually the fan chart that we get after we run the whole system like 1,000 times actually. So as you can see, it's clear that for certain nodes, you can see clear pattern or its trend between the nodes. As you can see here, for this graph, you can see it's clearly downtrend, and for this graph, it's clearly like the uptrend, right? And for the other certain of nodes, you can see the fluctuation between like I would say this line, and for the other nodes, they are also like the fluctuating, right? And this is more for the graph, and you can see almost all the, as I said before, almost all the nodes in our small system is kind of negative balanced. So most of the graph is actually downtrend, and for the other parts, or like the for certain of the nodes itself, when they are negative and positive is kind of balanced, it kind of we see like the fluctuation part, right? And then what we get is kind of we don't want like the random or whole bunch of random work to ruin our work, to mislead us. So we do like add more seeds itself to test our model. So what do? Is that we use 10 seeds, more random part, and take the average itself, and to see is it the real trend or just a random trend. So we do get more clear graph about the expectation part. As you can see, it's almost like the same as the graph that I showed you before, and for most of the graph, it's still downtrend, and for only some part of the graph, you can see it's uptrend and fluctuation. So this is kind of the interesting story. That's for certain of the graph, you can see like the asset price is still downtrending, which is obviously that's against the reality. So what we want to say is like a story. When a well-known scientist telling a story about a published lecture on astronomy and how the sun, how the Earth operates, the suns, and the old woman just said, "What you have told us is rubbish. The world is really a flat plate and supported on the back of a giant turtle." So the scientist gave a smile, and so what's the turtle standing on? And she just replied, "Just it's turtle after turtles." So which is also like our all like the value or the system detect one, and you can see that for almost all the nodes we do the rolling z-value analysis, and for most of value it's the standard deviation is over 2 standard deviation, which means that the whole system is like in a crisis and not that stable. So which means that which leads our maybe the discussion part. So are there any systematic error in supervisor like mental modelers we often like overshot our projections of long-term capital decay or long-term earning decay in regional settings. And these systematic errors, where they reflect a consistency pessimistic outlook on the future of the regional banking system. And maybe more strict supervisions. And examiners often unnecessarily strict due to these pessimistic projections. And also well-intentioned supervisors' bias might stem from the fear of the unanticipated economic downturns. And also maybe missing the stabilizing the structural elements. Like we often overlook the structure elements and could stabilize the system. Also, like robust local economics and diversification of assets and adaptive management practice. And which also have pros and cons, because pros is that this will encourage conservatism and possibly preventing risky behavior, better preparation for advanced scenarios, and leading to a more resilient banks. Cons, of course, over-regulation could stifle the growth and innovation and could lead to missed opportunities in leveraging, stabilizing the factors. Also, so for the future research questions, so why examiners are systematically pessimistic? And how can we balance pessimistic projections with realistic assessment? So, and others, like what structural elements should we better integrate into our examiners' models? So, that's all. Thank you, guys.
In the interest of time, I suggest you reserve your questions for lunch. So let's thank the speaker once again for a great talk.
Okay. Thank you.
But